Well, thank you for showing up on a Friday afternoon on this bright and sunny November afternoon. Before we get into today's talk, I'll just give you a teaser for next week. Next week we have a joint presentation as a part of the Inspire and Women Are Among Us events. We have Dr. Leah Torres talking about dots on a map, putting them to work for marine conservation. So mark that in your calendar for a week's time from today. Today I'm very pleased to introduce Dr. Brian Menounos. Brian is my neighbor upstairs in the hallway and talking about an exciting topic today. Brian's a professor in geography at UNBC and holds graduate degrees from the University of Colorado and UBC. He's also a Canada Research Chair in glacier change. And Brian's research program centers on improving our understanding of how past and present climate affects geophysical systems such as glaciers, lakes, and drainage basins. So I'll look forward to see which of the various areas he's working in he's highlighting today. Thanks, Brian.
Thanks, Darwin. Can everyone hear me? Great. Well, thanks for joining me in today's presentation. So I'm going to tell you a little bit about some work we've done over the last several years. I was hoping that I had a little bit more time to tell you about what's happened in the last year with respect to alpine glaciers. I'll give you sort of a snapshot, and stay tuned because we're still sort of compiling data from this particular year, as I'll allude to. Like any research program, I have to extend a very warm thank you to all the funding agencies, but most importantly, this stuff wouldn't happen without my smart students and collaborators. So they do the work, I just sort of come up and occasionally present it. So thank you very much. Now, when Darwin actually asked me to do this presentation on Monday, there was actually a cancellation. So he asked, did I have anything to present? And I said, well, I can do something. But what he hadn't realized when he asked about pinch hitting is that I was the strikeout kid. So as a Little League baseball player, the last game of the season, I was the last batter, and I struck out. So I hope I don't strike out today. Okay, so what I want to do before we talk about the summer and then talk about the fate of glaciers, I want to give you a little bit of a background with respect to the cryosphere. So we collectively think of the cryosphere as all the forms of frozen water on Earth's surface. And if you were interested in sea level rise, for example, you'd really want to pay attention to things like the Greenland and Antarctic ice sheets. So they're not going to melt overnight, but if in a couple hundred years, if you melt the Greenland ice sheet, we're looking at something close to 7 meters of sea level rise. Mountain glaciers and ice caps, it's a much smaller component, but almost 40 centimeters is expected to melt, or sea level equivalent, by the end of this century. Combining that with what is expected to come out of the Antarctic and Greenland ice sheets, then we're looking at something like up to a meter of sea level rise. Here's a graph that actually shows in terms of mass or gigatons. 1 gigaton is about 1 cubic kilometer of ice, and these are cumulative curves. And you can actually see that collectively for both of those ice sheets, they're contributing, or at least up till 2011, something like 11 millimeters of sea level rise. Of course, we also have thermal expansion of the oceans. Why do we care about this? Certainly from a societal standpoint, lots of people live close to the oceans themselves, and it's been suggested for every 30 centimeters of sea level rise, you have the potential to displace something like 50 million people. That's a lot of people, and mobilizing those people over the next century is quite a substantial problem that society faces. Okay, let's get closer to home. Western Canadian glaciers, why do we care? It's not really necessarily a sea level rise potential, so something like 8 millimeters of sea level rise if you took all the glaciers in Western Canada and melted them overnight. But that water, in many cases, supplements these headwater streams and can provide cool, plentiful water for aquatic ecosystems. So that's one of the primary issues of importance for these glaciers. In some cases, it's a transboundary water issue. So the Columbia Basin, as I'll show you an example, that water starts as glaciers and snowpack in the headwaters of the Columbia and flows out through the Columbia River near Portland. And also for myself, I'm really interested in climate. So glaciers themselves provide this excellent repository for how these particular frozen masses can adjust their dimensions to changes in climate of the past. This is a great comparison shot taken almost a century apart of Robson Glacier. Who's been up to Robson Glacier? Sadly, I have not. I've seen it from a carbon-belching helicopter, but I have not actually. I was hoping to get there this summer with my kids, maybe next year. So we see lots of those comparisons, and as we'll get back to this point, what's driving this change is largely warming at the lower elevations of the glacier itself. There have been, in some cases, some changes with respect to precipitation, but by and large, as we'll see, it's really warming of the lower elevations of these particular glaciers. So a glacier system, in the simplest form, high up on these mountains, we have snow that accumulates and collects much more than it melts during the summertime. And so that snow piles up, it accumulates, it gets thick enough to start to compress, change into ice, and essentially deform under its own weight. And really how that deformation occurs allows the glacier to flow to these lower elevations. So those lower elevations melt more than they accumulate. And it's really that accumulation up here that supplements or provides the mass to these low elevations. If we actually change the temperature, or in some cases change precipitation, then we can change these glaciers. In some cases it doesn't happen immediately, so we have to talk about a reaction time of the glacier. But essentially what's happened in the last 100 years is we've warmed up the atmosphere, and as a result of that, those glaciers are adjusting to that change in energy. Okay, so hydrologic implications. If we were to think about a large, even a small watershed with lots of glacier cover, let's say 50% glacier cover, as those glaciers are melting during the summertime, they're adding flow to these rivers that are typically fed by the winter snowpack, or in some cases precipitation. And as those glaciers decline in area, the contribution of that glacier runoff gets progressively smaller. So in terms of hydrology, it's not only the change or the reduction in the melt from these glaciers, but it's also a time change or a shift to earlier runoff conditions. And that's what several scientists have been able to show, is that there seems to be this earlier melt period as the glaciers get smaller, but also that winter snow cover is thinner, melts faster, and as a result, that exposed ice starts to melt away. People used to brag about how much energy one could melt with carbon, with petroleum products. Hubble is the precursor of Exxon, and so back in the 60s, they actually thought it was pretty cool to say how much energy they produced with respect to melting glaciers. You can imagine that you'd be fired by your PR firm if you came up with this particular ad today. Okay, let's shift gears a little bit. I want to talk a little bit about the blob. Who's heard this term, the blob? Okay, so it's appeared a bit in the media. The blob is essentially this unusually warmer than average pool of water off the coast of Western North America. And this thing's been hanging out. It's starting to dissipate now, but we have these times where we get warmer and cooler than average surface temperatures. So when you look at something like this, it says, well, it looks a couple degrees warmer than average. Well, how unusual is that? it's actually pretty unusual. So this is a time series of this area here for the last, well, at least until back to 1860. And what's particularly noticeable is that during the last year and a half, we've reached those values, those warm conditions that we haven't seen in that record, and it's also been a sustained period. So you can see that sometimes back in the late 30s, we may have had 1 or 2 months, but it really is an unusual event that we've had off the coast of Western North America with respect to sea surface temperatures. If you look at the geopotential height, so this is essentially a record of where the persistent high and low pressures are, what we see associated with that blob is a strong ridge that coincides essentially right over that warmer than average. So that's essentially an area of higher than average air pressure. And so as a result, we expect less storm conditions over that region. And that's one of the reasons as well that people have suggested that the East Coast in this last winter and the winter before was unusually stormy, is because of this deflection of the storm track. If you looked at the air temperatures, the 850 hectopascals is more or less at about 15 to 2,000 meters, so more or less where glaciers like to live in this part of the world. The temperatures, those air temperatures are also warmer than average. So it's partly due to drier conditions, but it's also been warmer than average. So things that we would expect to see with persistent high pressures or high pressure anomalies. This is a snowpack record, so a snow pillow. In some cases, the Water Survey or the Environment Canada puts down these pillows that are filled with antifreeze, and they can actually record the weight of snow up in the mountains. And they use these to come up with an indicator of how the winter snowpack is like. This Wolf River, this is a site on Vancouver Island, and this was the last year's snowpack record. You could see that it's the lowest on record. And indeed, it's really in this May to June period that it was unusually warm. But many of you have probably heard in the news that during the winter time, in many cases on Vancouver Island, they didn't experience any snowpack whatsoever. So quite an unusual event. Doesn't do good things for glaciers. So this is work that my team has been doing. Ben is doing a PhD. Rob back there, he's my LiDAR technician. So they've been actually doing some work in the Columbia Basin. These little stars here represent glaciers that Ben is monitoring as part of his PhD. I'll just show you Yoho Glacier here. This is some LiDAR that we actually flew in last September. And this is LiDAR is laser altimetry, so it's quite a sophisticated laser that's flown with an aircraft, and it gets you phenomenally cool DEMs, so these surface models, very high resolution surface models. This is what the glacier looks like, or looked like last year. This is what it looked like this September. I'll just flip back a little bit between those, and you can see how, if you look up here, these sorts of analyses or maps can give you an indicator of flow rates. But if you difference those maps, you can also get a surface elevation change. And when you integrate it over this particular glacier, you get something like 2 meters of water equivalent surface lowering. To give you an idea, that's about 2.5 times of what we have seen in the 1985 to 2000 period. So it does seem like it's been an unusual year. Okay, so I'm going to switch gears here. I want to now talk about the future and how glaciologists and atmospheric scientists try to better understand the future. What you're looking at here is you're looking at a general circulation model, one put out by UCAR in Colorado. And this is the CCSM model. I'll run it one more time. And what you're seeing here is you're actually seeing water vapor. The warmer the colors, the more water vapor. What it's showing you is the representation of storm systems as produced in this numerical weather model. These are run, of course, in the future to give us an indicator of how the climate is likely to change. So things like surface air temperature, precipitation, other fields. And have you guys heard about these representative concentration pathways? We used to, in the old IPCC assessments, one used to refer to things like emission scenarios, A1B, A2B. They've sort of, for the most recent assessment, they've adopted a different nomenclature in which the RCP represents representative concentration pathways. These essentially mean how much energy is expected to be put into the atmosphere. So we can still think of low emissions, this 2.6. This essentially means 2.6 watts of additional energy by the end of the century. So that's the good news story. The bad news story would be sort of this high end. So this is if we continue with emissions largely abated, and in fact they continue to increase due to population growth. So that's essentially what people or scientists use in driving these atmospheric models forward in time to come up with these scenarios. We're going to come back to these points when I show you some of the end results. Now, one of the drivers of the work that we were doing in the last couple of years is trying to understand not only how are glaciers going to change, but one of the hypotheses is that with enhanced greenhouse gases, you tend to get a more energetic atmosphere. And a more energetic atmosphere can hold more moisture and water vapor. So you would expect from physical principles that as you increase CO2 levels, you would expect to see an enhancement of the hydrologic cycle, largely due to increased precipitation. And so one of the research questions was, would this enhanced precipitation counter effect the warming at lower elevations? If you fall asleep before I get to the end of the story, I'll tell you that it doesn't. Okay, the warming surface temperature largely is much more powerful in sort of controlling the fate of these glaciers. There's a little bit of a punch, there's a little bit of a positive kick with the precipitation, but it doesn't last very long. What you're looking at here on these maps are the differences between, I'll call it the good news story and the bad news story. So this is high emission, this is low emission. These are the changes in the percent mean precipitation for these particular regions. This stippled area, it's a little hard to tell with the light here. This means that over 90% of the GCMs agree. So it really seems to be only under the highest emissions that you get general agreement, but the sign is consistent and suggests it's something like on the order of about 15% increase in precipitation for our part of the world. Okay, this is essentially a digital elevation model of Western Canada. This is the area that we did some of this modeling. I'm gonna just dim the lights as I try to show this here. But that's essentially about a 200-meter resolution. And you can see a certain amount of, oh, that's a little too light. Okay, you can see there's a fair amount of structural grain here. If you want to grow glaciers on this landscape, you're going to grow them on these real high peaks, these high elevation areas. Now, it takes a lot of computation time to do it at that sort of resolution. This is what a typical high-resolution general circulation model or global climate model sees. So you can see the problem here. If you tried to grow glaciers on this sort of landscape, you get these blobs in certain areas. You wouldn't get glaciers appearing in the landscape which we typically see with that topographic complexity. So that's one of the challenges that we faced. Now you can do it with sophisticated models. That GCM that I showed you, you can use a different type of model called the Mesoscale weather model, and you can run it for a year at very high resolution. This is his output at 1 square kilometer. The problem with this, and this is in the Columbia Basin, this shows snowpack, or snow depth rather, and you can see that in the areas that you would expect to find high or thick snow cover on the highest elevations. It seems to get it. It seems to also get some things like orographic precipitation, so enhancement with elevation. The lee sides of mountains tend to have less precipitation. The problem is that this takes about, in order to do a one-season run, it takes about 4 months of compute time. So if you want to do this for 30 different GCMs for 12 different emission scenarios, you've got a real challenge to do it on the planet. So we're not even close to having the compute cycles that you need to do high-resolution dynamical downscaling for the planet. So that's one of the challenges that we still face. So you have to think of doing it some different ways, and I'll give you some examples of how we did it. This is work that was in large part spearheaded by Gary Clark and some postdocs that worked with him. It also, Sean Marshall at the University of Calgary did some work, but I won't show that today. I'll really concentrate on the work we did with Gary. To give you an idea, the area that we did this modeling, this is Western Canada, here are some other regions on the planet that host mountain glaciers. You can see that by and large, the Alaskan Yukon area holds the lion's share. And fortunately, I also don't have Eastern Canada in here. So the areas around Ellesmere Island and the archipelago up there, that hosts almost as much ice as the Gulf of Alaska. So those two regions, they contain a lot with respect to sea level. Again, for our part of the world, Western Canada, it's more of an ecosystem and an ecosystem change with respect to those glaciers. Here's the domain just shown again. This is the area that we were working here, this region here. And what we did is there's a range of things you want to do. So that GCM that I showed you, or the different GCMs, that's this top box here. And you have to come up with a way to what's called downscale the precipitation and the temperature. So the two main ingredients that you would use to grow or nourish these or deplete these alpine glaciers. So you have to have a way to take those low resolution climate fields and get them down to a much higher resolution at the glacier scale. In addition to that, you have to, if you want to do any modeling, you have to understand the underlying topography of these glaciers. So if you're going to nourish these glaciers at the surface, once you nourish them, now you have to figure out, well, how is this glacier going to deal with this added mass or reduction of the mass? So you have to come up with a numerical model or some way to account for flow of the ice and how that will change through time. Once you do that, you have to know the underlying bed, and you run this through an ice dynamics model, and then basically you update the topography, the surface topography, and it's an evolving thing. Okay, so there's a number of things in there associated with that. The first thing that you need if you want to run a model or come up with a way to model the fate of glaciers, you have to understand the current extent of glaciers. And this is work that former postdoc of Roger Wheat and myself did using Landsat images. So from those Landsat images, Tobias was able to actually look at the different spectral reflectance of snow, basically in the Landsat imagery, and be able to semi-automatically delineate the glaciers in the province. It seems like it's not that bad of a deal. Well, it isn't bad for 1 or 2 Landsat images, and that's typically what you see in places like Europe. But in our part of the world, Tobias had to use something like 44 individual scenes. So it was quite an onerous task before him. But he was able to do this and able to actually calculate out the differences or how those extents of glaciers have changed through time. This is useful for people to understand how these glaciers are responding to the current climate, but with respect to the modeling that we were trying to do, we also need to have a starting point to understand the extent of glaciers if we want to actually model them forward. And so you can see that by and large, most of the ice is, with respect to British Columbia and Alberta, is contained within British Columbia. It's largely in the St. Elias and Coast Mountains. Those are wet, high elevation mountains, so they receive a lot of the precip coming off the Pacific Ocean. So when you look at the percent difference, you say, gosh, Alberta lost a quarter of its ice. Well, it starts with a small amount. So it's a numbers, it's a closed distribution problem. It doesn't start with a lot, loses a little, it seems like a lot percentage-wise. But by and large, if you were talking about the volume or area change, it's really the BC that had the greatest area difference. Okay, I want to move on and now talk about the downscaling approach, and then just conclude with with how these glaciers are expected to change. As I mentioned, ideally, what we'd like to be able to do is use the most sophisticated models, like a global climate model, or that model I showed you to do the Snowpack. Unfortunately, though, because it takes so much compute time at high resolution, it's just physically not possible to do it. And it's probably not going to be possible for the next decade or two to do it at that sort of resolution. So you have to rely on either statistical downscaling, find some functional relation between the low resolution fields, and come up with a way to get it to a higher resolution based on statistical relations. Or you have to do it dynamically. As I said, that's computationally difficult. We can't do that for our domain. So we decided to use a hybrid approach. And this is sort of a combination between some understanding of the physics and dynamics, and we couple this with some statistical relations. And one key, or one useful tool that we use to do this is we use an intermediate resolution product that is readily available for North America, but you can also get these sorts of products throughout the world. The one that we used here was the North American reanalysis. And this is basically a product that represents the current state of the atmosphere at a particular time in the past. And so this is a collection of observational data. Those data can include things like surface temperature. In some cases, it can include precipitation. In some cases, and in many cases, it includes tether sound, so some understanding of the relation of humidity, temperature, and pressure as a function of elevation. So if you go to any of the airports on the planet, a lot of airports will put up these balloons, these weather balloons. So all of this information gets put into these models of the atmosphere to come up with these homogeneous products on a sort of a given resolution every 6 hours. And so from that information, you can get things like the pressure, the temperature, the precipitation. So these can be used to drive models of precipitation in mountains at a much higher resolution. And that's what one of Gary's postdocs did in terms of trying to come up with a nourishment of the glaciers. I won't get into those details, but suffice it to say that this particular reanalysis product was useful to do the precipitation work and come up with that downscaling. I'll show you an example of the downscaling for temperature. This is what the NAR product looks like, and again, it's 32 square kilometers. You wouldn't want to try to go, even though this is higher resolution than the GCMs, it's still relatively coarse. This number scale is Kelvin, so 273, that's about 0 degrees Celsius. Once you actually apply the statistical relations that were found in the data, you can come up with a much finer spatial pattern of temperature. And this is for just the mean annual temperature for the year 2000. Okay? And you do this day by day, and then you actually have a distributed temperature field. You do the same thing for precipitation. And now you have the two fundamental fields that you need to nourish or deplete these glaciers. So how do you take these temperature and precipitation fields and grow glaciers? Well, one thing that you have to do is you have to, I'm getting ahead of myself. I'll tell you about that in a second. I forgot that I need to tell you about the subglacial topography. Here's an example of a representation of the glaciers near the St. Elias. So anyone who's been up to Tweedsmuir, this, I believe, is Tweedsmuir Glacier here. So these are fairly large glaciers. There's a relation between the steepness of ice and the thickness of ice, and some other variables that I won't have time to discuss. But knowing this relation, you can actually strip away those the ice itself to come up with the underlying topography. And you need that in order to actually grow these glaciers. You need to know what the underlying topography looks like. And so Gary Clark, again, he's a emeritus professor at UBC, he did some work to come up with this way of subglacial topographic inversion. It's not a unique process. Many different groups around the planet have done this for even places like the Greenland and Antarctic ice sheet. And you can actually show that by and large, it's a fairly good approximation. The best thing is to have radar, but at the scale of an entire mountain range or a region, you just don't have enough money to go out there and measure the ice thickness for the entire mountains. There's something like 16,000 glaciers, so to do one radar survey takes a lot of effort, as Rob knows, doing it a couple of years ago. Okay, I told you that I was going to tell you about you. So you get these temperature and you've got precipitation. Well, how do you actually nourish these glaciers or deplete them? You take these fields at a daily time step and you can put them into what's called a mass balance model. This is essentially a model that allows glaciers to receive an excess amount of mass or snow or be depleted at their low elevations. And so this accounts for things like the daily temperature, and whether that precipitation occurs as snow or rainfall. And it also accounts for energy that the surface feels due to solar energy. So solar radiation is also accounted there. And so these sorts of models tend to do a fairly good job at distributing or getting the elevation at which the accumulation and melt equals, so the equilibrium line altitude. It tends to get the distribution of melt for the low tongues correct. In some cases, they don't perform exceptionally well in the accumulation zones due to some factors that we won't get into. But by and large, the testing that was done for at least Western Canada seemed to suggest that it doesn't do a bad job, okay? It does seem to be one model that can be used to come up with adding material to the surface of these glaciers. Okay, so I'll conclude with just talking about their fate. And you probably know from the title, extinction, that it depends on where you're looking in the province, but I'll show you some graphs in a second here. If you wanted to say something about the glaciers, just if we were sitting down and we somehow had a understanding of their thickness and we knew how much they were on average melting over the surface, we could come up with a back of the envelope estimate of their lifetime. You just take the thickness and you divide it by the average melt rate. So that's the average lowering on average for that glacier. And so if the glaciers are not equilibrated with climate, and in fact, if they're losing more mass than gaining, then that number is going to be a negative. Vancouver Island, we don't have good data yet to say. There's very small glaciers, so we're not really sure how long those glaciers will last. But if you take these other regions, these mountain regions, and you look at the rates, you look at the thickness, you get something like a lifetime that's more or less about a century. Now, this doesn't account for dynamics. This doesn't account for how glaciers adjust and flow under their own weight. So there's this feedback that can occur. So this is just a first order estimate, but as I'll show you, it's actually not a bad estimate. It seems to be about a century for a lot of these particular mountain regions. We used different GCMs. We didn't use all the global climate models that were available. And I'll show you a couple movies. One from this MyRock ESM. This is the Japanese GCM. Just gives you the surface resolution here. And different countries have different GCMs that they invest and have invested, in some cases, many millions of dollars to contribute to the collective assessment reports from the IPCC. I'm going to skip those two equations. This basically just tells you how you take those the surface fields from the GCMs and relate it back to a high resolution field, but we already talked about that. I just put this in for anyone who likes math. I know Eric likes math over there. This basically just to remind me not to tell you about the math, but to tell you how the model for ice dynamics or deformation works. You can envision, everyone, some of my students know I love to do interpretive dances. Okay, here's a column of ice, right? You can run these models in 3D. That's what a GCM does, it's running in 3 dimensions. You can imagine this column and many columns together, but also individual slices through the column. That's a true 3D model. That's what the GCMs do. In our case, for the ice dynamics, we just use one column. And we say it's vertically integrated. So what we're interested in is knowing the stress to figure out how much ice flows and what direction it flows. So the surface or the bed topography will set whether ice from this column goes to you, comes back to me. Okay, so they're basically individual columns. That's what the vertically integrated means. And then we just conserve mass. So in this case, it just says that the change in thickness equals how much material we add to that surface minus the amount going in or going out of this side of the column or that side of the column. That's all it says. And basically, we run this forward in time, of course, perturbing this through time based on the input from the GCMs. And this is okay, so this is basically looking into Garibaldi Provincial Park, so about 50 kilometers north of Vancouver. You're looking at, year by year, the modeled extent of the glaciers through time. And you can see there's variability from year to year. This is what we would expect. I'll run it one more time before I do the, see if I can. Okay, so you can see there's some variability in the extent of these glaciers. But by and large, for the good news story, this is the low emission. We tend to be, we still see some ice in this part of the world. Okay, let's try that one more time. Okay, here's the bad news story. So this is very high. This is the high emission. Sadly, we seem to be on this trajectory. It's hoped that we get off of it. We'll see next month whether they can make any, or this month, I guess, whether they can make any decisions. So by about 2100, there's not a lot of ice left in Garibaldi. There's a little bit here and there. It's actually worse for our part of the world. So this is sort of the summary graph. You can see now we've sort of represented this as the coast mountains, the interior, and the Rockies. Again, this blue line represents the low emission, this red represents the high, and then the bands represent some uncertainty. But you can see both with respect to the ice area and the ice volume, even under moderate emission scenarios for the interior mountains, so the Caribou closest to us or the Rockies, we've already committed largely to their fate. So unfortunately, the emissions that we've done in the last 30 to 40 years, and will continue to do, has largely sealed their fate. So you can vary the percentage a little bit. There's not a lot of additional difference here. Now, the coast mountains, it's a different story. Something like even moderate emissions, we still have about 1/2 of the ice left by 2100. So if you like glaciers, I would recommend that you move to St. Elias Coast Mountains. Okay, I'll conclude with just putting up some summary points. So the work for this summer is still work in progress. So we're still collating and analyzing LiDAR data that we've done for a number of different sites. Also, Ben's PhD work on the observations does seem to suggest that it was truly an unusual year. So whether it's a window into the future, we can't say because it's a singular event, but it is consistent with what we would expect under a warmer climate. We just don't have the compute cycles to do this in at the highest sophistication that we'd like to. So using 3-dimensional models at very high resolution. So you really, the future really does depend on using some sort of hybrid approach. And this wetter climate hypothesis does not seem to counteract the increased warming at the lower elevations. And so by about 2100, we're looking at something like 90% of ice loss in the Rockies, more like 50% in the coast and St. Elias. So thank you very much for listening.
Back, want to hit the lights to full again? Either that or plunge us all into darkness. I always hit the wrong switch. Yep, that's the one. Any questions for Brian?
Roger.
Thank you. So before the most recent warming, there's been several cooler and warmer periods, which presumably were not caused by humankind. So what's stopping one of those cooler cycles coming back and completely changing what's currently projected?
So I should repeat the question, shouldn't I? Oh, we're good. Okay. So what's stopping us going back into a next little ice age, let's say? Nobody knows. Nobody knows. But based on the current greenhouse gas emissions and levels, I mean, we're seeing levels that we have not seen for a long, long time in terms of the geologic record. So back when we were having little ice age, CO2 levels were nowhere near what they are now. So I would say that what's stopping us from going into the natural century scale variability or back into a cold period is largely the enhanced greenhouse effect, that we simply have too much CO2 into the atmosphere. If we could actually suddenly sink it away, then sure, that natural variability would still happen. And it will happen. It's just the question of if you've reached a tipping point at which your enhanced greenhouse gas is so much that you have no glacier left. I mean, you can get these decades where the glacier make a little bit of an advance, but it's not going to counteract what we've seen.
There was some interesting information released by NASA this week or last from the gravity satellite showing a significant net increase in ice in Antarctica over the past couple of decades. Would you like to comment on that?
Yes, that's actually that was the paper, the Journal of Glaciology paper, right? Yeah. So our group has actually had an energetic discussion about that. This is work by Zwally and co-workers. This is so for those of you that probably, I mean, haven't read this paper, I don't know why you would, but so laser altimetry is, again, it's a laser. I was showing you stuff that's flown with an aircraft. This is flown from aboard a satellite that circles the planet. So you get these individual profiles, and what they showed is that, in fact, over the last, I can't remember how many years it was, 5 or 6 years. Anyway, over the last several years, they've shown, or at least based on their observations, that there's been a thickening of the Greenland ice sheet. And they're suggesting that the component is not adding to rising seas, but rather taking a little bit away. It's one of the highest, it's at the high end of the assessment for the Antarctic ice sheet. So a lot of other groups have suggested that it continues to lose mass. Why those things could be different are different methodologies, so they're not dealing with compaction of the snow. So how you represent how that snow melts into water depends on the density of the snow. So you have to make some assumptions on the density. You have to make assumptions on isostatic rebound too. So as that surface melts away, the underlying topography rebounds as you remove the weight of the ice. And so isostatic effects may be playing a part. But, I mean, it's important to note, too, that this is how science proceeds, is by having a range of measurements. Nobody's going to believe one method, and certainly not a measurement without uncertainty. So, but it is provocative.
You started your talk looking at water balance going into, say, a river, and saying this was the proportion that glaciers contribute to those flows. And if we're losing most of our glaciers in Western Canada by 2100, have you calculated what that's going to do to the Fraser, to the Columbia, to these major rivers?
We have, we actually, a lot of what I'm showing you here was we published earlier this year, and we did talk about the Columbia Basin. Now, I'll say it's an important caveat in that we didn't have a true hydrologic model, and so we're just basing it on the volume based on the modeling of what's no longer there. So if you take those melt curves and you take the first derivative, then you can actually get this hydrograph. And it seems to suggest that the peak water from this wastage of glaciers is like 2040 or so. But that doesn't account for storage, doesn't account for some subtle things in that a hydrologic model may actually be able to account for. There's been some other groups. There's a European and an Alaskan that just wrote a paper in this journal called Earth Frontiers, where they actually talk about the Fraser River as being incredibly sensitive to the loss of glaciers. And they have like a vulnerability index. But I'll try to get you that paper. It's actually an interesting read. But no, we haven't really fully gone a step further and put this into a true hydrologic model. So hopefully it's something we could do. Maybe work with some biologists or something.
Maybe I'll give you a last question here. So moving from ice and water to politics, do you think we have the technology or the means or the political will to move us off that worst case scenario?
No. Sadly, I don't. I'd like to think it's different. I mean, just today, Obama just said no to Keystone XL. I think, though, that until we find alternative energy that has the same muscle power, I mean, the problem is I'll use the analogy that we all like to recycle. We all like to have our to-go cups. We point out at people and say nasty words if they're walking from Starbucks with a to-go cup. But we're also not those types that, refuse to get into our cars. Some of us do, but it's a lot easier to recycle and use your to-go cup than to do the harder things like give away your car or make some serious serious decisions that I think affect people. It would be great to see the collective do that, but call me a pessimist. I mean, I feel a little hypocritical, flying around. But I also don't have a problem paying more for my carbon as a tax. But a lot of people they don't have that will, I don't think.
Well, we'll see where that debate goes with our new government. Thank you very much for coming on a Friday, and have a good weekend.